In this video, we're going to be talking about graphs of polynomial functions and cubic functions. So let's talk about the difference between polynomials and non-polynomial functions. The graph of a polynomial function is continuous. So essentially this means that the graph of a polynomial function has no breaks, no holes, nor gaps. It's got nice, smooth curves. So unofficially, you could say that a graph of a function is continuous when its graph can be drawn with a pencil without lifting the pencil from the paper. Let's look at some examples and we'll see what this means graphically for us. So here in our first graph, we can see, let's try that again. Here we have a polynomial function because it's continuous and it has gradual turns. Let's take a look at our second graph. What do you think? Did you say not continuous? You're right. It's not a polynomial function because it's not continuous. Take a look at our third graph. What do you think? Does it look continuous? Are there any breaks? Any sharp turns? Here we have a polynomial because it is continuous and it's curvy, right? We've got those gradual turns. Let's take a look at our last example, this fourth graph. So here we have something that looks like an absolute value function. So is that a polynomial or not a polynomial function? If you said not a polynomial function, you're right. And the reason is because it has a sharp turn. And that's a problem. Let's take a quick look at our cubic function. Notice here that on our cubic function, the center of our graph is at 0, 0, and it has points at 1, 1, and -1, -1 that they go through. Our graph has a domain of all real numbers, and it also has a range of all real numbers. It increases from -infinity to +infinity. It never turns down. It's always moving up from left to right. It's considered an odd function, and it has origin symmetry. So that means like we could turn it around the origin and it would be symmetric. So what is standard form for a cubic function? Well, standard form for a cubic function would be f of x equals -a times mx minus h quantity cubed plus k. And each of these pieces does something to our function and modifies it from our original parent function of f of x equals x to the third. Let's take a look at what those pieces might be. So here we're going to see that our negative sign in the front is going to reflect across the x-axis. Our a performs either a vertical stretch or shrink. It's a stretch if the number is larger than 1, and it's a shrink if the number is between 0 and 1. And it's a stretch or a shrink by the factor of that exact number. The m performs a horizontal stretch or shrink, and the stretch here is when our number is between 0 and 1, and our shrink is when our number is larger than 1. And here, it's done by a factor of the reciprocal of m. Our h is going to move the graph either left or right. If we see a plus sign inside those parentheses, it's going to move to the left. If we see a minus sign, we're going to move to the right. Notice how that horizontal stretch and shrink and that left and right movement seem kind of backwards from what we were doing before, what it seems like it should be. What I like to think of is when it's on the inside of the parentheses like that, it's lying to us. It's the opposite. It's like it's incarcerated or something like it's, and so it's a liar. Let's take a look at k. K moves it up or down. If we see a plus sign, it'll move up, and if it's a minus sign, it'll move down. These are the same movements that are used for absolute value functions, for transforming quadratic functions, for transforming linear functions, transforming exponential functions, pretty much all functions. And so it's important to know what each of these pieces do. Let's do a little example where we've got some graphs, and we're going to describe the graphs, and then we're going to sketch them by hand. Okay? Maybe not necessarily in that order. So the first thing that we need to know is, what is our parent function? We're going to call it g of x, which is x to the third power. That's our parent function. Our parent function will have a point at 0, 0, at -1, -1, at 1, 1, and then our graph is increasing. Here, we're given f of x equals negative x to the third. Notice that our negative sign is out in the front. So this should represent a reflection across the x-axis. So when we go to graph that, we'll still have our points at 0, 0, but now we'll have a point at -1, 1 and 1, -1. Let's make that a little bit bigger so it's a little bit easier to see. And so here we have our f of x in red and our g of x in green. And we can see that it's been reflected across the x-axis. Let's take a look at letter B, which is a little bit more complex. We'll start by graphing our parent function, which is g of x equals x to the third. So we'll have a point at 0, 0, 1, 1, and -1, -1. Here, we see that we have a point in the negative, well, in the h's spot, and it's a -1, so that should be going to the right 1. Then we have a +2 in the back, so it should also be going up 2. And so here we have right 1, up 2, so that's us describing the graph. And now we'll sketch it. So we're going to take our center 0, 0, and we're going to move it to the right 1 and then up 2. We'll also take our 1, 1 and move it right 1 and up 2. And we'll take our -1, -1 and move it to the right 1 and up 2, as indicated by our 3 red points here. Now we will graph it, increasing from left to right. And here we see our f of x now being transformed right 1 and up 2.